Hello everybody, Hobo here, and today I will be talking to you once again about the area of a circle. So let us have a circle, but this time it's different. It's embedded inside the Cartesian coordinate plane, specifically R2. And what we'll do here is we'll describe the equation of a circle, and then we'll break the circle up into certain parts, and we'll integrate the function to find the area of a single of those certain parts, and then we'll multiply by a certain number to evaluate the area of the entire circle. So let's begin. What's the equation defining a circle in the Cartesian coordinate plane? Well, we know the circle as y squared plus x squared is equal to r squared. And if we put that equation simply in terms of y, then we have y is equal to plus or minus root r squared minus x squared. That's a square. Yes. And if you're wondering, the reason why I put down plus or minus is because if the equation were simply defined as y is equal to the square root of r squared minus x squared, the positive square root, then that would only parametrize the top two quadrants. So it would only parametrize a semicircle and not a full circle. But in fact, a semicircle is what we want. So we're going to forget about the plus or minus, and we're going to forget about the equation that defines the entire circle, and we're going to look at only the top half. So we're going to look only at the positive square root. So let's forget about the minus. Wonderful. So we have y is equal to the square root of r squared minus x squared. And now we wish to evaluate the area of this function from, let's say, the x value 0 to r. And that's easy because if we evaluate this area over here and forget about the area in the second quadrant, so we only look at one quadrant, and one quadrant of the circle actually. So then all we must do is find this area. Let me call that area AQ for area quadrant. And AQ times 4 is equal to a total, or a tote. Wonderful. So let's find the area of the function going from 0 to r. Well, that's easy because all we must do is integrate it. Not so easy, but let's integrate it. So we have the area of a quadrant is equal to the integral from 0 to r of the function root r squared minus x squared dx. And well, now we can do some interesting things. We can, for one, factor out r squared from the square root and the integral. So then we have the area of our quadrant is equal to r times integral from 0 to r of the root of 1 minus x squared divided by r squared times dx. Let me erase all of this here except for this last bit. Okay, and well, how do we evaluate this integral? It's a fairly complex integral to evaluate. Fairly complicated. You shouldn't say complex for complicated in mathematics. You'll confuse it with imaginary numbers. So it's a fairly complicated integral to evaluate, but we have our trigonometric friends to help us because let's say that we substituted in sine squared theta is equal to x squared divided by r squared. Then we have 1 minus sine squared theta, and 1 minus sine squared theta is equal to cos squared theta, or cos squared theta. And then everything works out so perfectly. So let's actually make that substitution, because that's a very good step. So we have x squared divided by r squared is equal to sine squared theta. And what is theta? Theta is just a new variable, and we'll go back to what it means later. So we have x squared by r squared is equal to sine squared theta. Well, if we plug in that substitution over here, then we have our integral is equal to r times integral 0 to r root 1 minus sine squared theta dx. And you'll notice that I preserved that infinitesimal there, and that will turn out to be very important later on. So, well, what is 1 minus sine squared x? Sine squared theta? Well, we discussed that fairly recently. That was equal to cos squared theta, or cos squared theta, and the square root of cos squared theta is equal to cos theta. So then we have area of a quadrant is equal to r integral 0 to r of cos theta dx. And now you say, well, this is weird. I'm integrating a function that is in terms of the variable theta, but now you're giving me an infinitesimal in dx. So what we would like to achieve is an integral simply in terms of theta. So we have to take this dx somehow and rewrite it in terms of d theta. So, well, how do we do that? We go back to the equivalence, the equation that describes the relation between x and theta. So that is this here, and we can rewrite this. It's much simpler. So we can rewrite it as x is equal to r sine theta. And now let's do something interesting. Let's take the derivative with respect to x on both sides of this equation. So then we would get 1 is equal to r cosine theta. And because of implicit differentiation, I know my terms, I'm a big calculus boy. Then we get d theta by dx. And we can actually treat this d theta by dx like a fraction. So we can take this dx and multiply it on both sides of the equation, and then we would get, what would we get? We get dx is equal to r cosine theta d theta. So wow, we just calculated the expression for dx in terms of d theta. So now we can plug that in to our integral and evaluate. So times r times cosine theta, and once again times d theta. And well, what does this evaluate to? We can determine, let me rewrite this limit over here. So, well, we can take this r out here, and it becomes r squared. So let's erase that r. And then we have cos theta, so that becomes cos squared theta. Wow, everything's falling into place. And then we have cos squared theta times d theta. So let's bring that d theta closer. And we have our integral, which is area of a single quadrant is equal to r squared times the integral from 0 to r of cosine squared theta d theta. And this is wonderful because we have an easy trigonometric function to integrate. And for those of you who don't know how to integrate this, we use the double angle expansion of cos 2 theta. So let's take cosine 2 theta. And well, cosine 2 theta can also be written as 2 cosine squared theta minus 1. And then we can isolate cosine squared theta in this equation, because what do we do? Well, we add 1, and then we divide by 2, so then we have cosine squared theta is equal to 1 plus cosine 2 theta divided by 2. Wonderful. So now we can rewrite our integral and in terms of cosine 2 theta, because that is most definitely an easier integral to evaluate. So let's bring this back. So let's go there. And and the area of a quadrant is then equal to r squared, integral from 0 to r, of 1 plus cosine 2 theta, all of that divided by 2 d theta. So now let's erase all of this here to free up some space. Area of quadrant is equal to that. And so then we can evaluate this integral easier, and what does that become? We can factor out this half over here, and we get r squared by 2 times integral 0 to r of 1 plus cos 2 theta. And, well, integral, we can split that up. Integral 1 d theta plus, and multiplied by everything. So, plus integral 0 to r of cosine 2 theta d theta. Yes, so now let's close our end parentheses, and then we have this wonderful integral here, and this integral especially I like very much because it's very simple to evaluate, and it's theta. So now we have r squared theta divided by 2, and then plus r squared by 2 into the integral of from 0 to r of cosine 2 theta times d theta. So let's evaluate that. Well, the integral of cos 2 theta is equal to half sine 2 theta, and then we can plug that in, so, and multiply it by r squared by 2, and we have plus r squared by 4, because we take 2 here and 2 here, r squared by 4 times sine 2 theta. And since this was an integral, and since we're evaluating it with limits, we'll have to take limits, so 0 r. And you might say, well, we've had a change in variables because we went from x to theta, so it's not right to keep the variables, to keep the limits 0 and r. But let's save these for later, because what we're going to do now is we're going to substitute back x in terms of, or theta in terms of x. So if you recall what we defined theta to be, we defined theta to be x squared divided by r squared is equal to sine squared theta. So this then implies that x is equal to r sine theta, and x divided by r is equal to sine theta, and then we can isolate theta by taking the sine inverse, or the arc sine. So x over r sine inverse of x divided by r is equal to theta. So now we can plug that expression in to theta, and we can evaluate. So if we have r squared theta by 2, then if we plug in theta, we'll have r squared sine inverse of, let me keep this and simply rewrite it. So r squared sine inverse x by r by 2 plus, and then r squared by 4 times sine of 2 theta. and theta is equal to sine inverse of x divided by r. So then we have sine of 2 times sine inverse of x divided by r. That's a mouthful. So let's write it out and let's simplify it. So sine 2 theta is equal to sine times 2 sine inverse of, and I'll just continue over here, of x divided by r. So sine times 2 times sine inverse of x by r, how do you evaluate that? Well, sine 2 theta is can be rewritten as 2 sine theta cos theta. So we rewrite this as 2 sine theta times cos theta, or cos theta, whichever you like. And, well, theta is equal to sine inverse of x by r, so 2 times sine theta is going to equal simply 2 times x divided by r. So then we have 2 times x divided by r times cos theta times cos theta. Well, what is cos theta then? Because we have cos of sine inverse of x by r, which is also a mouthful. Well, then what we can do is we can draw a triangle. Call this angle theta. And then since sine inverse of x by r is equal to theta, so this must be x, and that must be r. So then what we get is this leg is x, the hypotenuse is r, this is a right triangle, and we have the other leg, the remaining leg, is equal to the square root of r squared minus x squared, because of the Pythagorean theorem. So then the cosine of theta is going to equal root r squared minus x squared divided by r. So then when we multiply everything together, we have 2x by r times root r squared minus x squared divided by r. So then we have, and this is only for this guy here, we're evaluating sine 2 theta right now. So then this equals 2 times x square root r squared minus x squared divided by r squared. And then when we multiply that with this, when we multiply it by r squared by 4, then the r squared and the r squared cancel out. The 2 and the 4 cancel out to become a 2 on the bottom. 2 on the bottom. And then we have this entire term is equal to x multiplied by the root of r squared minus x squared divided by 2. So let's rewrite that. Times plus x root r squared minus x squared divided by 2. And so then we have simplified our area from theta, from terms in theta, to terms in x and r. So this is wonderful because now we can bring back our original limits. And if you remember our original limits, because we're taking only the quadrant, the first quadrant of a circle, and we're taking it from 0 to r, then our limits become 0 to r. So then we have our final expression to evaluate. And well, what is this? So we take x is equal to r for this entire expression, and then we subtract the expression when x is equal to 0. So let's evaluate for our x is equal to r first. Well, if x is equals r, then sine inverse of x by r is going to equal sine inverse of 1, as we all know, is equal to pi by 2. So then we have pi r squared by 2 is this term. And now, well, we're getting pretty close to the area of a circle. Oh wait, no. This is pi r squared by 4. My apologies. Yes, we're still getting pretty close to the area of a circle, because the area of a circle we all know is pi r squared. So now we have pi r squared by 4 because we took pi by 2 times r squared by 2. And now let's evaluate for r is equal to x again in this term. So if r is equal to x, then the root of r squared minus x squared is going to equal to 0. So then this entire term for x is equal to r is equal to 0. So plus 0. And then what we do is we subtract this entire expression when x is equal to 0. Well, if x is equal to 0, then sine inverse of x by r is equal to sine inverse of 0 is also equal to 0. So this term is equal to 0. And then when x is equal to 0, this term is also equal to 0 because we have a coefficient of x. So then we have minus 0 plus 0. So plus 0 minus 0 plus 0, yes, okay, whatever, we get it, it's 0. So what we're left with is this term here, pi r squared by 4. Now, what did we come up with? We came up with, if you remember, the area of the first quadrant of the circle, the first quarter section of the circle. So what we must do now, since area quadrant times 4 is equal to area total, we must multiply this by 4. And when we multiply pi r squared by 4, what do we get? We get pi r squared is equal to a total. And thus, we have derived the equation, or, well, not really the equation, the formula for the area of a circle. Thank you very much.